let's talk about the criteria for precipitation. So basically, a lot of times what I want to know is when will an ion begin to precipitate out of solution? Okay, that oftentimes is a very important question. So again, if you don't want to form gallstones, you need to know what the concentration of the oxalate ion is in your blood, okay? So that you know to control your diet to try to reduce that. So precipitation, again, is simply another way of looking at solubility. It's just the opposite, right? So precipitation is just the opposite of solubility. So evaluation of the reaction quotient is going to help us determine whether or not a particular salt is going to precipitate or not at given concentrations of the ions. So to predict the direction of the reaction, we're going to compare again Q with K. So again, exactly the same way that we did in chapter 15, right? So the reaction quotient, again, has the same form as the KSP expression, except the KSP, in the KSP expression, we use the equilibrium concentrations. In the reaction quotient expression, we use the initial concentrations. So let's try an example. So let's say we have iron 3 hydroxide. Again, hydroxides are generally insoluble, so only a little bit is going to actually dissociate into the iron 3 plus and the hydroxide ion. So the reaction quotient expression is going to be the concentration of the iron 3 raised to the first times the concentration of the hydroxide raised to the third. And again, we're going to ignore the pure solids, so there is our reaction quotient expression. Again, the I's represent the initial concentrations, as where in the K expressions, they are the equilibrium concentrations. Now, if QC is greater than KSP, now you got to think about this, right? If Q is greater than KSP, do I have too many or too few products? If Q is greater than K, do I have too many or too few products?
Too many.
Too many, right? Again, it's products over reactants, right? In this case, the reactants don't appear, but it's products over reactants. So if Q is too big, that means I have too many products. If I have too many products, the equilibrium is going to shift back to the reactants, which in this case is a solid. Therefore, if Q is greater than K, it's going to precipitate out. It's going to precipitate out until equilibrium is reached, right? Not all of it's going to precipitate out, but it's going to precipitate out until equilibrium is reached. And in this case, there's very small amounts of the iron 3 and the hydroxide in solution. If Q is less than KSP, that means more salt can actually dissolve in the water and dissociate. And if Q equals KSP, which is, of course, means we're at equilibrium, that means we have a saturated solution. Okay? Okay, any questions on how to interpret Q for precipitation reactions? Okay, let's try an example then. So if the concentration of lead 2 is 1.2 times 10 to the negative 6 molar, and the concentration of arsenate, ASO43 minus, is 3.8 times 10 to the negative 8 molar, do you expect lead 2 arsenate to precipitate? Now, you might be thinking right now, the solubility rules do not address either lead 2 specifically or arsenate at all. So how am I going to answer this? Well, same way you would determine whether something's an acid or a base. In this case, you're just going to look up the KSP value. If it has a KSP value, it must be an insoluble salt and must be a weak electrolyte. So I'm simply going to look up the KSP value then for the lead 2 arsenate that would form, right? So from the tables of chemical data, the KSP for lead 2 arsenate is 4 times 10 to the negative 36. So not very soluble at all. I know that the reaction is going to be, so here's my lead 2 arsenate, right? You got to know how to name compounds and write formulas. So here's the lead 2, which has a +2 charge, right? It's the lead 2 has a +2 charge. The arsenate had a 3- charge. So again, if we just switch the coefficients, that means there's going to be 3 leads. And then we switch this one, that means there's going to be 2 arsenates. So there's our lead 2 arsenate, and we're showing it as dissociating, because that's what the KSP is all about, right? It's the dissociation of the salt. So it's going to dissociate into the 3 lead ions and the 2 arsenate ions. So again, do your homework so you can write these chemical reactions very quickly. Okay, so again, we want to know, is the lead 2 arsenate going to precipitate? So that means we got to compare Q to K. So we need to know what the initial concentrations of the lead in the arsenate are, and we need to know the reaction quotient expression, which again is just going to be the concentration of lead 2 raised to the 3rd times the concentration of the arsenate raised to the 2nd. That's what we see here. The initial concentrations of both were given. Now in this particular problem, we don't need to multiply them by anything because it's telling us these are the concentrations. So we're just going to plug that concentration 1.2 times 10 to the negative 6 for the lead 2 plus, and the 3.8 times 10 to the negative 8 for the arsenate. Still got to cube and square those values, and that gives us a value of 1.2 times 10 to the negative 27. So with lead 2 ion and arsenate concentrations as given, will lead 2 arsenate precipitate out of solution? Is Q greater than, less than, or equal to K? Is Q less than, greater than, or equal to K?
It's greater than.
Greater than, right? By 11 orders of magnitude. It is much, much greater than. So is a precipitate going to form?
Yes.
Absolutely, right? So if we have way, way, way too many products, it's definitely going to go back to reactants. And yes, a precipitate is going to form. Since Q is greater than K, a precipitate will occur. Okay. Any questions about that? Okay. Let's talk about solubility and the common ion effect. So the importance of the KSP becomes apparent when we consider the solubility of one salt in a solution that has the same cation or anion. Okay, I say the same cation, but it could be the same cation or anion. So for example, suppose you wish to determine the solubility of lead 2 sulfate in a solution that already contains sodium sulfate. Now, we don't care about the sodium sulfate, right? That's a strong electrolyte. That's a salt with the group 1A metal sodium in it. So we know that when we throw sodium sulfate in the solution, it's going to completely dissolve and completely dissociate. So what we're really concerned about here is the lead 2 sulfate. We know that that's an insoluble salt. Again, according to rule number 4, most sulfates are soluble with the exception of silver, mercury, lead, and then calcium, strontium, and barium sulfates would be insoluble. So this is what we're concerned with, but we're going to have an additional sulfate in our solution. So again, both of these salts contain this sulfate. Okay, so again, like I said, sodium sulfate's a strong electrolyte, so we're not worried about it, but the lead 2 sulfate is not completely soluble in water, so we're going to have to figure out how the solubility of the lead 2 sulfate is affected by the presence of this common ion, the sulfate. The sodium ion, again, don't care, right? It has nothing to do with lead 2 sulfate. It's a non-hydrolyzable ion, so it's not going to affect anything. So we want to know then, what is the molar solubility of lead-2 sulfate in 0.25 molar sodium sulfate? The KSP for lead-2 sulfate is 1.82 times 10 to the negative 8. We're going to need to set up the ice table. So it's the lead-2 sulfate dissociating into the lead-2 plus ion and the sulfate SO4 minus ion. Again, we're going to assume that we started off with, well, we're not starting off with pure water this time, right? What would be the initial concentration of the lead?
Zero.
0, right? There was no indication that any lead. But what is the initial concentration of the sulfate?
It'd be equal to the initial concentration of the sodium sulfate.
Yeah, right. So since it's 0.25 molar sodium sulfate, the sodium sulfate completely dissociates into one sodium ion and one sulfate ion. Therefore, the sodium would be 0.25 and the sulfate would be 0.25 molar. So in this case, this sulfate is 0.25 molar. It's not just 0. Okay. Change, well, we're going to gain one. Again, we're always assuming it's going in that direction. So we're going to gain one lead and we're going to gain one sulfate. So plus X and plus X for both. Equilibrium, we're just going to add up our initial and change. Our KSP expression is just going to be the concentration of the lead raised to the first, the concentration of the sulfate raised to the first. We're now going to plug in our KSP value of 1.82 times 10 to the negative 8. Remember what we're looking for, the molar solubility. So what am I looking for? What am I going to be solving for here? If I want the molar solubility of this lead-2 sulfate in a solution that already contains sulfate, what is the molar solubility? What are we solving for? What's the molar solubility?
It's just equal to X.
Yeah, X, right? X is the molar solubility. X from the ice table is the molar solubility. So we're just solving for X. So we're going to plug in the value for the KSP, X for the lead, 0.25 plus X for the sulfate. Okay. Now you're going to have to solve the quadratic formula, or let's start off by assuming that we could ignore the plus X term. And then again, we're just like we did before, we're going to come back and check to make sure that that was okay. So again, we're going to start off by just ignoring the plus X term. That gives us a value of X of 7.28 times 10 to the negative 8. You need to go back and check that your assumption was correct. And when we take 0.25 plus 7.2 times 10 to the negative 8, the two sig figs, I get 0.25. So our assumption was correct, right? Our assumption was correct. So that means the molar solubility of lead-2 sulfate in 0.25 molar sodium sulfate is 7.3 times 10 to the negative 8 moles of lead-2 sulfate will dissolve per liter of solution that contains 0.25 molar sodium sulfate. That is the molar solubility. And again, I stress this value of the molar solubility is when it is in a solution that contains 0.25 molar sulfate. If the 0.25 molar sulfate wasn't there, I don't think I give the value. I do. Okay, so again, like I said, this is the solubility in a solution that already contains 0.25 molar sulfate. So in pure water, the molar solubility is actually 1.3 times 10 to the -4. So in pure water without any sulfate in it, it's 2,000 times more soluble than if it's in a solution that's 0.25 molar sulfate. So you can see how the common ion effect really affects the solubility of ions. Okay, any questions about that? Okay, let's talk about how solubility is affected by pH. So a lot of times we can change the pH and make something more or less soluble. So for example, let's consider barium sulfate. So barium sulfate, again, one of our insoluble salts, when we dissolve it in water, it will partially dissociate to form the barium ion and the sulfate ion. However, if we throw this into an acidic solution, if we dissolve it in an acidic solution, the acid is going to give up a proton to the sulfate to form the weak acid hydrogen sulfate. Well, hydrogen sulfate is not sulfate. So what's going to happen then is that as we remove the sulfate as hydrogen sulfate, it's going to dissociate more to try to replace that the sulfate that I removed as hydrogen sulfate. So in this particular case, because we have a conjugate base of a weak acid, we can increase the solubility by making it more acidic or decreasing the pH. If on the other hand, we had the conjugate acid of a weak base, we can make the salt more soluble by making the solution more basic or increasing the pH. Okay. Any questions about that? How could I change the pH for sodium chloride to increase its solubility? What could I do to the pH to increase the solubility of sodium chloride? Well, there's two issues with sodium chloride, right? Number one, it's a soluble salt, so it's already dissociating, but let's say it didn't. Well, the other issue is that the sodium ion is the conjugate acid of a strong base, so changing the pH isn't going to affect it. The same thing with the chloride. The chloride is the conjugate base of a strong acid, so changing the pH again wouldn't affect it. So again, it's only the conjugates of weak acids and weak bases that are affected by a pH change. Okay, so again, like I was saying, so as I add acid to it, it's basically removing the sulfate and it's causing the equilibrium to shift to more product to replace the sulfate that I took out. And so the solubility of the barium sulfate is going to be greater in acidic solution than it is in neutral solution. Okay, and again, that's just Le Chatelier's principle. Anything that I do, nature's going to try to undo. Okay, next let's talk about what's called fractional precipitation. So this is an analytical technique where if you have a mixture of ions, let's say you take a sample of ocean water, and you want to figure out exactly the concentration of the different ions that are in ocean water. Well, to do that, a lot of times you have to separate the ions because you can't, if you try to determine the concentration of one, you might actually be determining the concentration of more than just one ion because whatever titrant you're using reacts with more than one ion. So a lot of times it's best to try to separate the ions first. And we're going to do that by using the solubility rules, okay? So for example, when we slowly add sodium sulfide to a solution that contains copper and zinc ions, we're going to find that the copper precipitates first. And you'll be able to predict that. You'll be able to actually predict which one is going to precipitate first and at what concentration of the, in this case, sodium sulfide that you would need to add to precipitate out as much of the copper as you can without precipitating out any zinc at all. And we're going to do that by using the KSPs of the two salts that would possibly form. So here's the copper 2 sulfide, has a KSP of 1.2 times 10 to the negative 36. And the zinc sulfide that would form has a KSP of 2 times 10 to the negative 25. So we can see that the zinc 2 sulfide is 10 to the 11 orders of magnitude, 11 orders of magnitude more soluble than the copper 2 sulfide. So the one with the smaller KSP is going to always precipitate out first. Okay, so that's why we can predict that the copper 2 sulfide is going to precipitate out first, because it has the much smaller KSP value than the zinc 2 sulfide. Now, each has their own equilibrium constant expressions. Now, in this case, let's first look at the copper 2 sulfide solution. Now, well, I take that back. Let's say that we want to add a given molarity of the sodium sulfide so that we precipitate out the copper, but we don't precipitate out any of the zinc. So what I'm going to need to know is, well, what concentration of sulfide can I add that won't precipitate out the zinc? Well, the most I could possibly add when the concentration of the zinc 2 sulfide would be saturated, right? So I can have a saturated solution of the zinc 2 sulfide. I just have to figure out what the sulfide concentration would be at that saturation point. Okay, so how much do I need to precipitate out the copper? Well, there's 0.2 molar. That's the original concentration given to us. There's the KSP. And so 6.3 times 10 to the negative 36 molar. So I need that concentration or slightly greater, right? At this concentration, I would have a saturated sulfide solution. So that's going to be the minimum molarity to start precipitating out the copper ions. If I put now I want to find what is the concentration to precipitate out the zinc ions. Well, it's going to be, again, just doing the same thing, it's going to be 1.1 times 10 to the negative 24 molar sodium sulfide. So I could add this concentration of sulfide before any zinc 2 sulfide would precipitate out, right? This would be the saturated point. Now we could actually calculate exactly how much copper would be left in solution after I added this molarity to our solution that contains a mixture of copper 2 plus and zinc 2 plus, right? So we're just going to plug in the value for the saturated zinc 2 sulfide solution, okay? And then solve for how much copper would actually remain if that was the concentration of the sulfide ion. 1.3 times 10 to the negative 12. So in other words, there's almost no copper at all left in the solution, and it is primarily zinc at that point, right? 10 to the negative 12 compared to 10 to the negative 1 is 11 orders of magnitude difference now in concentration between the zinc and the copper. So again, that's all that's left of the copper, almost nothing. And we precipitated almost all of it out and just left the zinc 2 plus in solution for the most part. Okay, now many metal sulfides are actually insoluble in water, but dissolve in acidic solution. So for example, again, just by adjusting the pH, we can adjust the how much of a particular metal would precipitate out of solution. And usually we use hydrogen sulfide to do this. And the reason we do that is we can really control the concentration of the hydrogen sulfide. So when we put the hydrogen sulfide in water, it dissociates to increase the hydrogen ion concentration or the hydronium ion concentration. It makes it acidic, and it leaves behind the hydrogen sulfide. Now, the hydrogen sulfide will continue to dissociate, right, give up its acidic proton and form the sulfide ion. But as we've already seen, the concentration of that would be equal to the Ka2, which is really, really small. And as we're going to find out, we need small quantities, right? We're looking over here, we're talking about 1 × 10⁻24 sulfide ion concentration. So we need really, really small concentrations, controllable concentrations of sulfide to control our precipitation. So this has a really small Ka2 value, okay? So by simply controlling the pH of the solution, I can very, very well control the concentration of the sulfide in solution, okay? So by simply controlling the pH, I can control the sulfide ion concentration. So let's say we have a mixture of metal ions, and we're going to be able to separate them by simply exploiting the differences in the solubilities of the different ions using basically the solubility rules. Now, I'm going to show you what you would really use in the lab, the procedure that you would use in the lab. In the homework quizzes, exams, I simply want you to use the solubility rules that you already know to perform these types of tasks. And we'll do a homework problem like that on Monday, okay, or Tuesday, whichever day we get to it. Okay, so this can be done by simply using the solubility rules again, or we could use a much more specific set of rules as we're going to see. So this technique is called qualitative analysis. So qualitative meaning all we're doing is figuring out what the species are, not the concentrations. Okay, so let's say we have a mixture of metal ions and we want to separate these metal ions. So first thing we're going to do is we're going to add dilute hydrochloric acid. Well, remember, according to the solubility rules, the chlorides are generally soluble soluble with the exception of silver, mercury, or lead. So if I throw in a dilute solution of HCl, the silver, mercury, and lead are going to precipitate out. And then the filtrate, so basically what I'm going to do is I'm now going to filter off this mixture after adding the dilute so that I'm going to catch the solid silver, mercury, and lead chloride in a filter, remove it, and what's left is called the filtrate. So the filtrate is going to contain whatever other metals that are actually in the solution. So all soluble metal chlorides, right? So all the other metal ions that are in solution. Next, I'm going to add the sulfide in a relatively weakly acidic solution. Now, again, according to the solubility rules, we know that most sulfides are insoluble. So what's going to happen is I'm first going to precipitate out all the sulfides that are really, really insoluble. And I could even do this in stepwise, right? I could change this. I could make this just 0.1 at first and precipitate out the most insoluble sulfides and just keep increasing the pH and keep precipitating out the sulfides as they become more and more insoluble. So in this step, I'm just separating out all the sulfides that are really insoluble. Then I'm simply going to, this time, I'm going to add a base, which again is going to strip off all the H's and leave behind just S2 minus. So now I'm going to have a really high concentration of sulfide. So now I'm going to precipitate out any of the other metals that have a much greater solubility of the sulfides. Okay. So now whatever metal ions are left after all of this, I'm going to add either ammonium carbonate or ammonium hydrogen phosphate. So basically what I'm now do is I'm going to precipitate out any of the metals that are insoluble as carbonates and phosphates. And these two rules are almost identical to each other. So I could add either one. I don't need to add both. I could add either one and I'm going to get the same results. So I'm now going to precipitate out the barium, calcium, and magnesium and strontium because those carbonates and phosphates are insoluble. And now all I'm going to be left with are rule number one, right? Those group 1A metal salts. So lithium, sodium, potassium, rubidium. And now to determine what ions there are of those solutions, we could actually do a flame test. So basically you put some of the solution on a wire and you burn it in a flame, and the color of the flame will tell you what ions you have in solution. Now, again, we're not going to use this. We're simply going to use the solubility rules. And as you can see, this basically is using the solubility rules to do that, except they're just being a little bit more quantified by using different concentrations of different species. And then we're going to move on to chapter 18. It says, describe how you would individually separate an aqueous mixture of metal ions consisting of our copper 2+, mercury 2+, and barium 2+. Now, I can tell you that there's more than one possible route to this, and I would accept any possible route as long as it's correct. How would you go about doing this? First off, what are you going to need to know to answer this question? And again, you're not going to have time on the exam to use cheat sheets. That is part of this course, not only being able to solve problems, but to be able to do it proficiently. So what are you going to need to know to answer this problem?
I mean, I'm looking in the lecture and it says within qualitative analysis.
Yep, that's what this is.
But, okay.
Make sure it's soluble.
Say again?
Make sure it's soluble. Like
Okay, so how do you know what is would you know? How do you know what's soluble and not soluble? The solubility rules. So to answer this, you need to know your solubility rules, right? So we're going to try to precipitate out one ion at a time. So what could I add to this mixture, right? I have a mixture of copper 2+, mercury 2+, and barium 2+. What could I add to this mixture to precipitate out one of them and leave the other two in solution? Could I add sodium carbonate to the solution? If I added sodium carbonate, would any of them precipitate? Which this, of course, is a strong electrolyte because it's a sodium salt. So will the sodium have any influence on the solubility? No, it's a cation. The cation isn't going to react with other cations. So it must be the carbonate. So any of these metal ions precipitate out of solution if I add a carbonate solution to it. I could add sodium carbonate. I could add ammonium carbonate.
No.
None of them, nothing's going to precipitate out. Even though according to rule number 5 of your solubility rule says that most carbonates are insoluble with the exception of rule 1. So those group 1A metals, sodium, lithium, potassium, cesium, rubidium, and ammonium carbonate. That's why I used a group 1A or ammonium carbonate, because in that case, that is a strong electrolyte, and it's just basically freeing up the carbonate. So the carbonate's going to form a precipitate with all 3 of these. So if I throw in sodium carbonate right off the bat, all 3 ions are going to precipitate out. That doesn't help me. What can I add to this solution to precipitate out just one of these ions?
Could you use rule 3 where it talks about chlorides, bromides, and iodides?
Oh, okay. So now I don't want you to add any other metal ions. So this was actually a bad choice for me. But I could have used ammonium carbonate. That way I'm not adding any more metal. So what could I add to this then to precipitate out just one of those ions? And yes, you're on the right idea.
A chloride?
Yeah, but you can't add chloride because you can't buy a jar of ions. So what are you going to add? I agree, you want the chloride ion in there.
Could you just do like an ammonium chloride?
Yeah, you could throw in ammonium chloride, okay, NH4Cl, okay, that's cheap. You could throw in hydrochloric acid, that's cheap. Both of these are strong electrolytes and would dissociate into the ammonium ion and the chloride ion, in this case the hydrogen and the chloride ion, right? So generally we'll throw in HCl. We almost always have that on hand in the lab. So if we add HCl, the HCl is going to cause what to precipitate?
That's going to cause the Hg2 plus to precipitate out.
Exactly, right? Because rule number 3 says that most chloride, bromide, and iodide salts are soluble with the exception of silver, mercury, and lead. So that means this is going to precipitate out is mercury 2 chloride, which is a solid, leaving behind now the copper 2 plus and the barium 2 plus, right? So there was our step 1. Now what can I add?
Could you, to get the Ba2 out, you could add something with like a sulfate to it.
Okay, so ammonium sulfate.
Yeah, we could do that.
Okay, so NH4, 2. I could use sulfuric acid, right? It has the sulfate in it. Okay, now I'd have had to make the solution slightly basic because hydrogen sulfate isn't a strong acid. So I'd have to make it basic to rip off that hydrogen to give me the sulfate, but I could do that. And so what's going to precipitate out if I do this? If I add this, what's going to precipitate out?
Your Ba2 plus.
Right. Again, rule number 4 tells us that most sulfates are generally soluble, with the exception of the silver, mercury, lead, which we already got rid of, and calcium, barium, and strontium. So this is going to precipitate out as barium sulfate, right, is our solid. That would leave us with copper 2 plus. Now, how would I get it out of solution?
You could add sodium hydroxide.
Yeah, not sodium, though, because I don't want to add any metals.
Yeah.
So how about ammonium hydroxide? Okay, then that'll precipitate out then as the copper hydroxide. Okay. Could anybody think of some other route we could have taken? What if I would have added the ammonia hydroxide instead of this? Then the copper would have came out, but the barium would have stayed in because barium hydroxide is a strong base. Then I could have added a sulfate or a carbonate or a phosphate or a sulfide. Now, not a sulfide actually, because the sulfide, barium sulfide is soluble. So I couldn't add a sulfide, which also means I could have added a sulfide to get the copper out, which would have left the barium in. So you see what I'm saying? There's all kinds of different paths you can take. You just need to know your solubility rules. And I will take any acceptable path. Okay, any questions about any of that good stuff? So again, please make sure you're doing your homework, and please, if you have questions, ask me. I will be more than happy to do what I can to help you understand. Okay, so let's